Okay, which of these is a vector? So we need it to have a magnitude or a size and a direction. So distance, no. Force is though. So it's going to be force, B. Figure 17 shows a balanced seesaw. So it's in equilibrium. The pivot is at the center and it shows us that here. The child has a weight of 150 newtons. So we can see that there. It says calculate the moment of the weight of child P in Newton meters. So it wants it in Newton meters. That's in newtons. That's in meters. Perfect. So we've got our fat, moody dinosaurs for our turning moment. And for the child, it's actually going to be an anti-clockwise turning moment. But it tells you exactly what to do. Just got to multiply the two together. Is 217 Newton meters. Well, if it's in balance, we now know that she must be 270 Newton meters too. So figure 18 shows the same seesaw, and this time it gives us the distance to child Q. Calculate the value of W, so find out their weight. So we've got our fat, moody dinosaurs. We've got to use the idea, so this is just the principle of moments. The total clockwise moment equals the total anti-clockwise moment, and it says give your answer to two significant figures. So we want the force, which is the weight, and we can see that that's going to be the turning moment divided by the distance. The turning moment we had from the previous question, where we found out that child was 270 Newton meters, so that must be equal to this child's. And then we're ready to just put the numbers in. So we know child Q is 270 Newton meters. If we then divide that value by the 0.95 meters, we get 284.2. We want to go to two significant figures, so we look at the 8 and we look at the number behind it, and that's a round down, 280 newtons. Next one, figure 19 shows a crowbar being used to lift a heavy weight, and we can see we've got a turning moment again. And the basic idea is anytime I use a turning moment like this, I increase my mechanical advantage, and increasing the distance is a good thing because there's two things I can change. We know that the moment equals the perpendicular distance times whatever the force is. So if I increase any of those two things, it'll increase the turning moment. So it says explain how the crowbar enables the person to lift. So the basic idea is it's going to increase the distance. You should include the idea of moments in your answer, and it may help to label some distances. So what I could do to help answer this is I could say I've got distance 1 here, distance 2 here, and the same force. And the idea is that the bigger the distance, if I increase the distance, I increase the turning moment. You could even put numbers on here to prove your point. So I could go 2 meters, another 2 meters, and I could use a force of 1 Newton. And then I can say to D2 equals force times distance. So that's going to equal 1 times 2 equals 2 Newton meters. And then I could say for distance 1, which is further away, I don't know why I put a dot on that. So for distance 1, it's the same, force times distance, and that's going to equal 1 times 4, because the total distance is 4, equals 4 Newton meters. And then we get the idea, 4 Newton meters is greater than 2 Newton meters. That's a great thing. So with the same force, I've got an increase in turning moment. Here comes all the wording for it, but that's one way that you could have gone with labeling some distances. So it's easier to lift with a crowbar as it gives a mechanical advantage. The crowbar increases the perpendicular distance from the pivot, and there's some key words there, so distance and pivot. I'm just using what's in my diagram. We know that the moment equals force times the distance. Put it in. Always go to your equation sheet and add equations in. Increasing the distance gives a greater clockwise turning moment with the same force. Or another way of wording it is less force is needed for the same turning moment, but I'd stick with the top one there. And there you go.